To agree.
Oh,
So welcome everyone to this week's Origins Colloquium. It's a great pleasure to welcome Blakesley Burkett to give the talk this week. Blakesley is an associate professor at Rutgers and a research scientist at the Center for Computational Astrophysics, Flatiron Institute. She received her PhD from Wisconsin-Madison, University of Wisconsin-Madison in 2014. She was a postdoc at Harvard, Einstein postdoctoral fellow, and ITC fellow before starting her position at Rutgers in 2019. She has received a number of awards, Sloan Fellowship, Packard Fellowship, I think a few other fellowships that I'm forgetting now, but is doing incredibly well. And her research spans, as we'll see today, from very nearby clouds in the Milky Way to the very distant universe. So welcome, Blakesley.
thank you, Jonathan. And yeah, I'm very excited for this colloquium. I love the format of a shorter talk, but more time for discussion. And the work I'm going to show today, I'm very much hoping to get the community insights and input and discussion. And also, I know this is being recorded and put on YouTube. So if someone is watching this after the fact and has some ideas or insights or discussion, please email me or reach out, and I would love to continue talking about how we can really push our understanding forward on the molecular cloud gas star life cycle. That's what I'm going to be talking about today, and I'll particularly talk about the use of tracing directly the photodissociation boundary layers in molecular clouds using the far ultraviolet. So that's my focus today. If it's of interest to anyone, I can also talk about the high redshift aspect of that, but I've actually kind of left that out just in the interest of time and keeping the discussion
Mhm.
time preserved. And so I'll be talking about opening questions with regards to molecular clouds. And I think this is a bit of a point where the community's at an impasse as to how to answer some of these questions. On one hand, we have all these incredible observations of molecular clouds from the radio, submillimeter, and of course, JWST now in the infrared. But we still have so many open questions, which I think we need additional insight into another part of the electromagnetic spectrum, particularly the FUV. And so these are open discussion questions. We can talk about these after the talk as well. What the relationship between the molecular cloud life cycle, galactic environment, and star formation, the chemical lifetime of molecular hydrogen. So individual molecular hydrogen molecules, do the growth and destruction of those relate to the molecular cloud lifetimes, or are they kind of disconnected from that? Obviously, a big question is around stellar feedback and also galactic dynamics, and how do those two factors dissociate and regulate cloud formation and star formation. And I think we have lots of fantastic tools, both observations and numerical simulations, that have been helping us address some of those questions. But I really think to answer them, to really have definitive answers, we need to be able to see the inflow and outflow of molecular material, molecular hydrogen, at the boundary layers. And of course, we do have some ways to look at that. I'm showing you a cartoon on the right here of a photodissociation region, and you can see where it goes from the yellow kind of ionization front. We have atomic ionized tracers that can very well trace some of that material. And then, of course, as we go further and further in to where the cloud becomes shielded from external radiation, we can trace molecular material, of course, very well with CO, and even a little bit of the boundary layer with C+. But to directly trace that inflow of molecular to atomic material, we need to be able to see the fluorescing H₂. Of course, I'll talk about how we can do that, not just with the infrared, but also with the FUV. So just a little bit of background from your interstellar medium graduate class that you took either recently or very, very long time ago. You were taught that H₂ is difficult to observe directly, right? And that's because the H₂ molecule is a symmetric molecule. It has no permanent dipole moment. It has weak quadrupolar transitions that can be excited either collisionally through shocks or in high temperature regions, but they're very diffuse emission. It's not very bright transitions. And so, of course, then we use other tracer molecules to trace the bulk of the star-forming molecular gas, which is the H2, but again, we can't see it. So we'd look at things like carbon monoxide or CO to especially trace the mass of the clouds, which is predominantly that cold, denser gas. There's problems with CO. There's many, many problems with CO as a tracer and also other tracers. And I think visually, this simulation from the Silk collaboration, Steffi Walsh and Daniel Seyfried, really shows this very well. So this is a tall box simulation, a slice through a disk like the Milky Way. And here they run non-equilibrium chemistry where you can trace ionized hydrogen, atomic neutral hydrogen, the molecular hydrogen, and then the carbon monoxide. And just right away visually, you can see the volume filling extent of the atomic species is very large. It fills up a much larger scale height than the molecular gas. But comparing the molecular H2 and the CO, it's really striking, right? I mean, you see how much less volume filling the CO is. It's not really tracing the extent of the molecular material. Right, so I already mentioned, how difficult it is to observe molecular hydrogen. The infrared, obviously with JWST, there's beautiful examples of shock-excited H2. Those can be very great temperature and density diagnostics. But though, they trace shocks. They don't trace that photodissociation region necessarily. There are some examples, though, in the infrared with JWST where it is tracing that photodissociation region. And how is that? It's because H2 actually does have some dipole-allowed transitions when you excite it with fluorescence. So you have an external, in this case, Lyman-Warner photon, which is in the FUV band, that interacts with the H2 molecule, excites it into the electronic excited states, which then are dipole allowed. So they're actually very bright. And then once you have that excitation, you have a couple possibilities. One is that you'll have a series of transitions back into the ground state. And that will release a cascade of photons in the FUV and also in the infrared. And so JWST can see some of these fluorescing FUV cascaded down photons into the infrared in some very bright PDRs. And there is a couple examples of that. But again, you need a very bright PDR in order to do that. You wouldn't be able to necessarily look at, a molecular cloud like Taurus using that kind of infrared diagnostic. So what if we had a far UV telescope that had a kind of a large field of view, so you could map molecular clouds in the FUV, and you could actually directly see that fluorescent excitation of the boundary layer, tracing the H2 to H1 transition. And that's what I want to talk about today. Like, what if we had such a telescope? What would the community do with it? I have some ideas about what I would like to do with it and questions I would like to answer. So that's the idea of, tracing directly the H2 dissociation front and also the formation front with those FUV line diagnostics. So we actually, I was part of a proposed mission back in 2021 called Hyperion, which is a NASA proposed medium explorer class mission. So medium here is in relation to the cost cap of, I think it was around $300 million. So we were rated category 1, which is like NASA speak for like A+. Great mission, science is great, no major weaknesses. Usually in a normal mid-X competition or explorer competition, if you get a category 1, you usually go to like at least a phase A kind of exploration where they are like, okay, let's further develop this concept and maybe launch one day. But at that year, there were like 4 other category 1 missions. So they had to decide from there like which mission they're going to pick. All these missions were great, at least 4 of them. So we were unfortunately not selected. But the mission actually had many components. One is, as I will talk about in this talk, the molecular gas life cycle as traced by the boundary layer physics, looking directly at molecular hydrogen. But there were other aspects, more intensively looking at massive star feedback and also looking at protoplanetary disk evaporation. So it would have done everything from like molecular clouds to planets. We are going up for the next Explorer call, which is a smaller cost cap. Basically, the smaller cost cap, 175 million, means we have to nix the protoplanetary disk science because we needed a much higher resolution spectrograph to resolve the lines around the evaporating disks. So unfortunately, we can't do that with the tighter budget, but the molecular cloud life cycle science still remains. So we're calling this mission for the SMEX 2026 call EOS. EOS is the daughter of Hyperion in Greek mythology, so that fits very well. And just giving an idea of what Hyperion or EOS, the field of view in terms of mapping molecular clouds, right? We have a much larger footprint to where like Hubble, and you can see in this image is sort of like a degree or so of what Hubble would look at. It just like there's no way you would ever be able to, of course, map a molecular cloud with an instrument like Hubble or JWST. And so this is the need for this kind of mission is just a totally different optical design than what we have right now. So what have I been doing? I'm more of a theorist. So I've been working with collaborators such as Shmuel Bialy on understanding what we would observe, right, with this mission. One thing we would directly observe is H₂ dissociation rates, right? And so, of course, we can use numerical simulations and look at the true dissociation rate in a simulation and what, would be kind of an observed, if we did like a synthetic observation. And so here's these simulations are simple turbulent box simulations. But we have non-equilibrium chemistry, so we can follow the H1, H2 transition in a way that's at least chemically kind of realistic. The top row is different realizations of the 3D cloud along different axes. And then we have the true value or the true dissociation rate, which is just the total number density of molecular hydrogen times the dissociation rate. And then the middle row there is the observed value. And so the observed value essentially is proportional to the intensity in the FUV, modulated by absorption from dust. So that's also tracked in these simulations. And then the very bottom row is kind of a ratio of observed to true. So we can see like where we have, the bulk of the cloud and filamentary regions in the cloud, we can actually get a reasonable handle on the true value. Similar with formation rates. So there's several different ways that in the FUV we can get a handle on the formation rates. So, obviously in the simulation, there's a true formation rate. In the observed way that we're doing this, we can either look at line ratios of ortho to para H2. So that's the proton spin directions of the two hydrogen molecules. They give a handle on the formation rate. Here for the post-processing, we're actually using a method that Shmuel Bialy developed in a 2025 paper where we measure the formation rate using the total column density of hydrogen. And so this method also does a pretty good job of estimating the true to observed H₂ formation rates. So already we can start to answer a question, right? There's been a long-standing assumption, at least for the theorists, that molecular hydrogen formation and destruction is in some kind of steady state, right? There's an equilibrium assumption, and many chemical models assume chemical equilibrium or make these kinds of assumptions. And so right away with these sorts of observations, we can see that clouds are out of equilibrium, right? So the maps here I'm showing you are ratios of formation to destruction rates. And so you can just see they can be orders of magnitude out of equilibrium, especially in regions where you have filament formation going on. And so we would be able to test, equilibrium questions with FUV diagnostics. What else can these rates tell us about molecular cloud evolution? It's interesting to answer questions about equilibrium, but what else can we do? Well, if we make plots like this, where we have, let's say, formation rate over star formation rate on the y-axis and H2 dissociation rate divided by star formation rate on the x-axis, or I'll show later just the H2 formation versus dissociation rate plots. It's another way to look at it. Right away, you can start to diagnose a particular molecular cloud's state, whether it's in kind of an early phase of its evolution where it's growing from an atomic reservoir. If it happens to be in an equilibrium state, you would have sort of an equilibrium status between formation and destruction, or sources and sinks. And then finally, you would see potentially part of a parameter space where the cloud is actively being destroyed by FUV photons from newly formed stars, especially massive stars. So this parameter space, I think, would be very valuable to go out and make these measurements, place molecular clouds on this kind of diagram where we could see if they're in this growing regime, an equilibrium or steady cycling regime, or a dissociating regime. And so one thing I wanted to use, hopefully our discussion time later today, and I'll mention this shortly, is that different cloud evolution models will make different tracks on this kind of diagram, different predictions. And so it's another thing that the EOS FUV telescope could do, is make statements about competing cloud lifecycle models. So that was the points. I should mention the points here on this plot are from a single molecular cloud simulation from the Silk Zoom simulations. Now, what if we take an ensemble of clouds, and what can we say about clouds on a population level? And so to answer that kind of question, like global cloud evolution models, we've used Sarah Jefferson's really beautiful Arepo simulations that were published a few years ago to study cloud life cycle, where the clouds have Lagrangian tracer particles, which can enter or leave an H2 dominated state. So one can essentially track the formation and destruction of molecular hydrogen as Lagrangian particle tracers. So I think, yeah, next slide is cool movies from Sarah, showing gas column density in this isolated dwarf simulation, which is kind of an analog to NGC 300. And then you have on the right side the H2 column density, right? And you could also make a similar movie, although I don't have it here, of the CO, right? And again, you would see very similar to that Silk tall box simulation I showed earlier. The CO clouds are much less volume filling than the H2. But the CO is how we're going to identify molecular clouds in the first place. So I don't have a movie of the CO, but the CO in this case is going to be used to track particular molecular clouds. So there's an ensemble of clouds here, right? So there's, it's a disk, it's a disky dwarf galaxy. So we have, many dozens of clouds in this simulation at any one given time. And so we can follow their evolution as a function of mass. So we have mostly a lot of low mass clouds, some intermediate mass clouds, and a couple high mass clouds, basically following the kind of molecular cloud mass function that we would expect from the observations. And we can place these clouds on the formation of H2 on the y-axis and the destruction of H2 on the x-axis in a way that the FUV telescope EOS would potentially produce a diagnostic of. But of course, it's a simulation, so we can explore some other interesting things about these clouds that we would not necessarily be able to get from the observations, in particular, the relationship between JF and JD, as I'll call formation and destruction, with cloud age, right? And so this is something that Sarah Jefferson found in her 2024 paper, that low mass clouds live less time than high mass clouds. And you can see that right there in this diagnostic on the left, we have the low mass clouds. So they essentially at most kind of live maybe 10 megayears. Most of them live actually much less than that. They also populate lower values of JF and JD in that parameter space. As you go to higher mass clouds, the clouds live longer. So you can see in the color bar is changing. The yellow is going to higher and higher values as you go to higher mass clouds. But also the way that the clouds track the parameter space of JF and JD is changing, right? The overall rates, especially the formation rate, is much, much higher for high mass clouds. So right away, we would have a prediction that we would see high mass clouds, where they are in their JF/JD will look very different from low mass clouds. And then there's a relationship between where clouds are in that parameter space of JF and JD with cloud age. And we can dig into that a little further. So here's kind of a summary of all of the clouds. This is an average of all of them. They all follow these general kinds of tracks in formation rate on y-axis and destruction rate on x-axis, where they have initially early in their lives kind of a building phase. The cloud is being built up. Usually it's from an atomic reservoir if it's just slow accretion, but it's also possible to build clouds through cloud-cloud collisions or spiral arm motions. All of that is sort of represented there. There's an equilibrium phase where there's a rough kind of steady cycling of JF and JD. That phase actually tends to be kind of short. Most of the time, the clouds are not in equilibrium. And then in the red, there's a phase where clouds are dissociated. If we plot that as a function of mass, now mass bends, where we have low mass clouds, intermediate mass clouds, and high mass clouds averaged together, you see they track different parts of the JF/JD parameter space. Sorry, it looks like JD got cut off there on the x-axis. But this is extremely cool, right? Because if we go out and we make measurements of JF and JD, we can place them on this parameter space. We can measure things like cloud mass, and then we can place them on these diagnostic tracks, right? Where we can then make predictions about cloud age and cloud potential lifetime. So we've been thinking of these tracks almost like an HR-like diagram for cloud lifetimes, where we have measurements of JF, JD, we have measurements of mass, and we have predicted isochrones or cloud age tracks where we can place them on the diagram and then make a prediction for their age and also for their remaining amount of lifetime that they would have left, which then we can make really cool statements about star formation efficiency, et cetera, once we know how much longer the cloud may spend in its lifetime converting H₂ into stars. So how will the EOS telescope look in terms of this kind of diagram? Right, we will have measurements of molecular clouds kind of on the whole cloud face, the whole surface of the cloud. And so, we will have more low mass clouds than high mass clouds. That's fine. That's just how the molecular cloud mass function works. The low mass clouds, I think, are really interesting because they will populate a large swath of the parameter space towards hopefully low JF and JD values. We'll have just a couple high mass clouds, but I think, given the census of local molecular clouds and also local group clouds that are very high mass, like 30 Doradus, those kinds of things we can target, we'll be able to populate a large ranges of mass and star formation rate on this kind of plot. We will also be able to map what's happening inside a given cloud, right? So those are, each point on the right is a single, total JF and JD for a molecular cloud. But of course, then we can zoom in on a cloud. So I'm imagining one of those points in the purple there, those represent the low mass clouds. Maybe it's something like Lupus, which is almost starless. Maybe, and this is a simulation, but maybe Lupus will look something like this, where you have a lot of formation, very little dissociation, because there's no star formation yet. And Lupus has actually a very large H1 reservoir. So this is something like we might see in Lupus, versus something like Cygnus X, which would be potentially one of those yellow points up there, which would be highly star forming, a lot of molecular gas, very high values of JF and JD. These are the kinds of things we would love to go out and measure, right? This is a simulation, but at the end of the day, this could be a measurement that we could make. I'm going to skip this. This is, I think, what I'd love to discuss if people are interested in, like how potentially different cloud models, like a global hierarchical collapse model or a dynamically driven cloud evolution model, might make different predictions on this parameter space. That's something for later. I want to show, though, very quickly, I know I'm starting to get low on time here, a measurement we've already made without having to go build this telescope. One cloud we've been able to do this with to kind of demonstrate the proof of concept that yes, this can be done. And it's a cloud that was recently discovered by my team. We actually called it the EOS cloud after the telescope. And it was kind of found because I was super disappointed about the mid-X results. And I was looking at this current data set that exists. It's from the FEM-Sphere telescope, which is a South Korean telescope that was launched in kind of the mid-2000s. And it made a map of H₂ fluorescence at very, very low spatial and spectral resolution. I mean, the spectral resolution R of 500-ish, like the H₂ lines you can see are not lines at all. They're blended wiggles. So, we want to do much better with an R of 10,000. But this is the data we have. And so I was, looking at this data, investigating this data, and I saw this feature that I've circled in the top left there. And I was like, wow, what's all that H₂, all that molecular hydrogen doing up there at high galactic latitudes? And then I thought maybe is it associated with the North Polar Spur, which is the map I'm showing in the bottom left in the X-ray bands from E Rosita. You see this beautiful arcing large structure in galactic coordinates. This is the North Polar Spur. You also see it in X-rays and synchrotron. So it expands a wide range of the electromagnetic spectrum. It's a very prominent structure, and there's a lot of discussion about is it, a galactic center structure? Is it a nearby structure? What is it? So at first I thought that's very strange that you would have H₂ there. And then I looked at FUV continuum from the same data set from the FEM-Sphere, and there's no FUV continuum, right? FUV continuum will trace massive stars. So star forming regions, and you see nothing there. And if you also look at the ratio of the H₂ FUV fluorescence, so that top map to the bottom map, the structure really pops out, right? So you can kind of zoom in and see it has this nice crescent shape. And so I'm at this point like, okay, is this a single cloud? Is this a single object, or is it, maybe just a bunch of stuff along the line of sight? So to answer that, I went to Tavisha Dharmawardena, who at the time was a postdoc here with me at the CCA, and she's now a faculty member at Monash University in Australia. She's an expert on 3D dust maps, and I went to her and I said, Tavisha, tell me what this thing is. Is it something, multiple things along the line of sight, or is it something nearby? Is it a single cloud? And so sure enough, she looked in her dust maps, and we looked at the sight line towards this object, and we found that it's basically perfectly matched to the local bubble. So this is a hot local bubble. Local being the sun is sort of almost at the center, and the bubble kind of extends out to about 100 parsecs or so from us. And the cloud is sitting right along there with nothing kind of in front or behind it, at least out to several hundred parsecs behind it. And you can see the cloud kind of mapped almost perfectly with the dust, where the sort of top part of the contour of the cloud traced in the FUV is the closest, around 100 parsecs. And then the sort of bottom part here almost goes out to about 130 parsecs. So this is the first cloud. It's a local molecular cloud. It's a single structure. And it's the first cloud that's ever been found directly by looking at the H₂ in emission directly, right? Usually clouds have been found with dust or with CO. So this is a first example of that. And this was the movie I was showing at the start of the talk, where you have a kind of contour model of the local bubble in yellow, and then you have the 3D dust in contours mapped around that. You see a couple clouds we all know and love, like Perseus and Taurus and Lupus and Ophiuchus. And there's our new cloud EOS, and it's sitting right next to the North Polar Spur. I mean, they are like hugging each other. And I have a whole exciting talk about how I think the North Polar Spur X-rays are producing that fluorescence that we see in the EOS cloud. I don't think I have time to tell you that story, but happy to do so later. So when we published this result, it was published in Nature Astronomy earlier this year. We did a little press release, but like the New York Times picked it up. So for some reason, people, I thought at first when our mid-X telescope didn't get selected, like, oh, no one cares about molecular hydrogen, like, oh, why? Like, why me? Why? Oh, woe is me. And then when this result got published in the New York Times, I was just elated because it means, yeah, people do care about molecular clouds. People are interested in star formation. And they loved the idea that the cloud is fluorescing, right? I mean, really, it's not quite glow in the dark phosphorescence, but like they loved this idea of the fluorescent discovery of this cloud. So the New York Times picked it up, and then like everyone picked it up. So it just like went into the news, CNN, BBC. This was my favorite CNN comment. And then like New Jersey.com, so like my local news station loved the idea that not only was this press release really big, but like I just had my baby. That's a whole nother story as to why this press release and my baby came at the same time. It was
Is
not
your baby
planned.
also called EOS?
Baby is not called EOS. Baby is Corinne.
Oh, excellent.
But yeah, so that was just a crazy coincidence of timing. And to just further convince you this thing is really there. We have maps of the dust extinction, emission of dust from Planck. The H₁, this is from the Galfa survey. It's just beautiful. There's some decomposition methods that you can apply to H₁ emission maps now that can separate the cold neutral medium and the warm neutral medium. I don't have the map here. It's just so beautiful. This cloud just pops, not only in total H₁, but when you look at the cold neutral component, it's just, oh, it's amazing. And then the X-rays, right? The X-rays are a very interesting story, which I don't have time for. But you can see that the X-ray, soft X-rays, and also one keV X-rays, they're modulated by the shape of the cloud, right? So the cloud is sitting next to the North Polar Spur. The North Polar Spur X-rays, I think, are an important part of the fluorescent story for this particular cloud. There is a little bit of CO. There's a little cloudlet called MBM40. And if you, let's see, oh, I don't have that slide, but if you measured the mass of the cloud from just the CO, you get something like 20 solar masses. If you measure the mass of the cloud from the dust and from looking at the mass of the cloud as traced by the full extent of the H₂, you get something more like 3,400 solar masses. So the cloud is like more than 99% CO dark. So going just back to like this diagnostic plots that we would make if we launched the EOS telescope, since we have this example of the EOS cloud, we can apply that formation and destruction rate method to put it on this plot. So there it is. That's the little magenta star. It's squarely in the red, so it is dissociating rapidly. I think, again, the X-rays are an important part of that story. But if we just look at the timeline for the cloud in a little less than 6 megayears, this cloud will be gone based on the rates that we observe and also its mass. So we will be able to do this for many, many more clouds than just the EOS cloud, and to see kind of what's happening in their cloud life cycle. I was a little disappointed that the EOS cloud is dying. It has no stars currently. It probably never will form stars. So, sorry, EOS, you're going to die soon. So that's my conclusions. I definitely want to save time for questions. I'll just pop up, I think some of the exciting things we will be able to do with these observations. And yeah, take questions from there and discussion. Thank you.
Great. Thank you very much, Blakeslee. So basically raise your hands on Zoom if you have questions.
And
And
I can't see
yeah, I'll try and moderate for
there,
you
so
here. Yeah, I think it's good if you can keep showing things because probably we'll go to, you know,
yeah.
the slides. Um, yeah, Ayush, do you want to start? And I have a whole list of things here if we
Yeah,
need.
thanks, Blakeslee. Great talk. My question was a little bit basic. So you had shown that CO and AS2 had different volume filling factors. So when we use CO to trace AS2 masses, are we underestimating or we take that into account in observations?
That's yeah, I think it depends on the cloud. So for mass, most of for a regular cloud, I think EOS is a special cloud. I think for your typical Taurus or Orion or whatever, most of the mass in the solar metallicity universe is pretty well traced by CO. And that's because CO is tracing the cold regions of the cloud. And most by mass, most of the H2 is in that cold region. Less of that H2 is in the warmer boundary region. But CO, I think, is even in a regular cloud at solar metallicity, local universe, that's what I mean by regular cloud, is not tracing the volume extent of the cloud, right? And you could see that in the silk zoomed, the silk tall boxes or the zooms. Um, any simulation that follows the chemistry shows that very clearly that by mass, CO is doing a good job, but the volume extent of the cloud is not well traced by CO.
Mm. My memory is something like, what is it, thir about 30% or so of the
30 to 40% could be dark gas
CO
by
dot.
mass.
Mm.
Yeah.
Yeah. John, yeah.
Right. Thank you very much for a really stimulating talk. I'm glad to see this interest in the UV spectrum of H2. Um, I just wanted to point out, since during the last week, my head has been uh, in the space of low radio frequencies, uh, and especially looking forward to the square kilometer array going into operation and the Meerkat telescope already operating. It turns out that molecules like OH can now be detected and mapped with 100 times better sensitivity than in the old days. And this is an alternative, indirect way of mapping H2. And
Absolutely. Yep.
with molecules that uh, are better direct tracers of the H2 abundance in many ways. OH will tend to be present
Yep.
wherever there is molecular hydrogen and doesn't have the same sort of threshold for detectable abundance as CO. So that's one thing. But I also wanted to just sort of wonder out loud whether there's also possibility for doing ground-based observations with a well-designed infrared instrument to look for the infrared fluorescence of the molecular cloud surfaces. This
Yeah.
was done in some pioneering observations by Jaffe and Luhmann
Yep.
in the 1990s, where, for example, they showed that the total luminosity in the fluorescent emission of H2 of the Orion molecular cloud, or just the PDR surface,
Yeah. Yeah.
was much larger than the extremely intense high surface brightness stuff that's produced in the shocked regions
Yep.
in the core of OMC.
Yeah,
And
and
what
people are
one needs
now
is,
using JWST to look at that too, and it's beautiful. I mean,
yeah,
JWST can't map a cloud. It's a different science thing. I have lots of thoughts about your comments and so forth. So, I mean, like the Orion JWST observations I've seen from Karen Sandstrom, they're just absolutely beautiful. Like they really clearly show the infrared lines and the fluorescent cascade and the quantum mechanics of the lines. It's just exactly what the theory predicts for a bright PDR. But you would never be able to use JWST to map the cloud, right? So it's a
Yeah.
different science question we can answer. Same with OH. OH, to
Well,
your
it's a
point,
different, excuse me, it's a different technical observational question, because it is possible to design an instrument like the one that Jaffe and Luhmann used on a small scale. They had a tunable Fabry-Perot,
Mhm.
which gives you a very large field of view and at the same time high velocity resolution or high spectroscopic resolution.
I
So,
think the challenge would be sensitivity, right? Because the infrared
yeah.
lines, even from fluorescence, are much, much weaker.
Mhm.
And so the question is, down to what intensities in the infrared are you going to be able to see? And the FUV is much brighter. And of course, the problem with the FUV is you have to go to space, so it's expensive. But you'll be able to go down to much lower surface brightness PDRs if you go to space in the FUV than you would from the ground in the infrared.
Hmm. Can you
That's
remind us,
correct.
where was Jaffe using something on Mauna Kea or something? Or can you remember what instrument what facility were they using?
Well, they built the instrument, the the Fabry-Perot spectrometer, had a wide field of view, and it was their test instrument, as far as I recall, was um, um, not extremely sensitive
Hmm.
for the reason that they had a single element detector or a very small array. I don't remember which, but with modern infrared detectors and a well-designed stigmatic Fabry-Perot device, I think one could reach the sensitivity needed to see cloud surfaces of diffuse molecular clouds
Hmm.
illuminated by the general background UV
Mhm.
starlight. And keep it. You're quite right that in the UV you also have the advantage that the contrast between the line and any background continuum emission is greatly enhanced, whereas there's a lot of potential background in the near infrared. Um, but at the same time, it's important to remember that the fluorescence process produces 3 infrared line photons for every UV line photon.
Yeah.
So it's a fairly good yield, and if you're able to approach the photon detection limit.
Hmm. And then Blake, any comment on the OH that John also mentioned?
Yeah, I think, I mean, the OH, um, it's just tracing different aspects of the cloud, right? OH, I think, so you can't, as you know, but maybe not everyone knows, you can't use these FUV lines to trace mass. There's some papers that are very interesting in terms of using the infrared to trace H2 mass, but it's not a mass tracer. So CO, OH, those are going to still be the workhorses, especially the OH for tracing the CO dark gas. It will be a better tracer of mass. The H2 fluorescent lines can trace temperature. They can trace the radiation field. They're direct tracers of the radiation field in the Lyman-Warner band. So they just do different things
Yeah.
than the OH is doing. So I think we need both.
Mhm. Great. Gina.
Yeah, hi, Blakeslee. Great talk. So I was curious, in your ground truth plots of the destruction and formation rates with the individual molecular cloud, you showed that there's a factor of a few, error in the true versus the observed. So I'm curious, does it work in a way such that the ratio of those two is pretty on point, or do you, in the observations, will we have to deal with this uncertainty?
Yeah,
Of,
so I showed some of the plots with error bars, so that's kind of folding in that factor of a few. And the ratio plots, of course, will also suffer, right, from the similar kinds of errors that you would get from JF and JD. So there's always going to be some measurement error, right? And it comes also down especially for JD, it comes down to resolving the brightest H2 lines. That's where the predominant source of measurement error comes from, with that, and also what's happening with the dust. The good news on the dust side is we have beautiful 3D dust maps that help us understand the structure of the dust on the cloud surface. And yeah, so that's all of that will have to gets folded into the errors.
Can you pull up the figure, Blakeslee, that showed, I mean,
Yeah,
a simulation where you had a ground truth, and then you're saying when you do a synthetic observation, is it because of foreground dust extinction or something that, or what exactly is causing this error?
let me pull it back up. There we go. Doo, doo, doo. Yeah, so so the true dissociation rate is very simply just the number density of H2 times the dissociation rate. Okay. Now, the observations, there can be sort of a couple predominant sources of error or mismatch. One is the proportionality of the dissociation rate with the total intensity of the fluorescent lines. That total intensity depends on how well you resolve those lines, for one. So our calculations suggest you need about the 10 brightest lines resolved in order to make these kinds of maps. So that's one source of error. The other is extinction, right? So there's attenuation from dust, which is, especially in the FUV, it's very sensitive to that. And so how well we understand that attenuation on the cloud surface, and again, it's only the cloud surface we're looking at. We're not looking through the cloud. We're looking at the surfaces of the cloud because we're just tracing the boundary layer, and two, we also have the absorption by dust. So having those three-dimensional dust maps is very critical for kind of beating down what's happening in terms of the dust attenuation. And so you can see in this left equation, it's called equation 9 there. There's that e to the minus 1.9 times the total column, and that's essentially this attenuation factor from dust.
So is this because you're also jointly trying to fit to G0 at the same time, or if you knew G0, would your error be much smaller?
We don't need to know G0, although that helps, and that's interesting for understanding the excitation that we see in this from the the measured FUV spectrum. We can directly measure the the total intensity. Having an independent measure of G0, though, as I said, is an interesting factor for understanding if the excitation is coming just from Lyman-Warner photons, or in the case of the EOS cloud, right? I mentioned there's this possible X-ray excitation mechanism. And that's because if we look at kind of the interstellar background G0, it's not high enough to explain the bright fluorescence of the EOS cloud. And so, we then say, oh, well, okay, we have the X-rays from the North Polar Spur right next to it. That could be an additional source of excitation.
Maybe we can take one step back because I'm trying to make sure I've got it all straight in my head here. The formation rate of H2, you say you can measure. Now let me try and, so H2 forming on dust grains is then born in some excited state.
Yep, so there's a couple different ways we can do this. One is this indirect. So this synthetic observation we've made is kind of an indirect way. So this would not be relying directly on a EOS telescope observable. This is an indirect tracer that relies on total column density from H1 and dust. But there's another way, and I'll skip to like a hidden slide.
But let me just make so the H2 that's formed on dust is in some excited state, but it's nothing to do with the electronic state, right? It's just
So when H2 forms, it's in a preferred um, uh, orientation of the two protons. So it forms in an orthopara ratio of around 3.
Mhm.
And that's then from there can be collisions that reduce that orthopara ratio from 3 down to some equilibrium value. And so that's another way that directly from the FUV spectrum, we will measure the orthopara ratio of H2, and we can then say something about H2 timescales and formation rates.
Okay.
Yeah, I mean, in these synthetic observations, we didn't do the line emission modeling, so we didn't use the orthopara ratio for these particular maps.
So the formation rates are a bit more indirect than you're saying.
They're both in. Our plan is to use both indirect and direct methods.
So
Because the direct method is actually measuring the orthopara ratio. The indirect method is using this column density tracer.
Now I recall there was some discussion about H2 forming, via PAHs, and I'm trying to remember if that is different to process, or would you be sensitive to that?
Is that less? That must be less common than just dust grain formation, like typical dust grain formation. I don't know too much about that actually.
Yeah, I've forgotten it myself, but I remember people being interested in, there are some experts here who may know more than me, but I remember people discussing whether, because pHs dominate surface area, but it may be more of a chemical, dehydrogenation of pHs. But anyway,
If you remember some of the papers, that
yeah.
could be interesting to. Yeah, I don't know too much about that.
Okay, so then, but I want to come back to the question you raised about this, this long-standing debate about whether molecular clouds, form and are destroyed, within a free fall time, very fast, a few million years. So if, say, a giant molecular cloud, 10 to the 5 solar masses, was rapidly built up from H1 in just a few million years, how exactly would we distinguish that from a cloud that is really sort of sitting there for, is more in this sort of chemical equilibrium state?
Yeah, I mean, so this is what we see in these isolated disk simulations where I think I didn't mention that there's, supernova feedback, there's FUV dissociation of the H2 from massive stars, and winds as well from stars. So there's various feedback processes modeled here. How would we distinguish that, right? So, when we go out and observe a cloud, we can already tell if it's massive, right? So that already gives us a hint as to where to place it, where we might expect it to be placed on this plot. Now, when we go out and we look at it, we say, okay, we have a JF of, a few tens of solar masses per megayear. Okay, interesting. So it's a high mass cloud. We see where it is on the JF-JD plot. Let's say it's in the green. We would be able to place it on a predicted track here, right? If we go out and we see a low mass cloud and we see it in that part of the parameter space, very, very high JF that looks like this simulation's high mass clouds, we would say, oh, there's something wrong with our models. Like there's something wrong with how we're modeling feedback or cloud building, or we're missing something. So that's also an interesting thing to find out, that our simulations are woefully, wrong in terms of what a real cloud would look like on this diagram. In order to connect it to lifetime and like how long it's going to live and the free fall time of the cloud, that would be where the modeling tracks come in, right? I mean, we have the mass of the cloud, we would have its average density, we could compute a free fall time. We know where it would live in terms of, oh, it's rapidly building H2, it's not destroying H2 as much. Or, if it's in the red part of this diagram, oh, the cloud, it's still massive, but like we can already make a prediction based on its measured dissociation rate, how much longer it has to live. And that's exactly what we did with the EOS cloud, right? We were able to make a statement about the cloud lifetime and the cloud, death time based on the measurements of those rates.
But the numbers I'm remembering, you definitely see it discussed. A giant molecular cloud might form in just less than 10 million years or a few million years, and then on the y-axis here, the rates would be wouldn't they be off the plot here? So,
I think in this case, it depends on the cloud mass,
right,
right? As
but
to how much, I mean, the very massive clouds, so like greater than 5 times 10 to the 5, they can live in these simulations, they live for longer than 50 megayears. And that's
right.
not just because of accretion of H1, it's also because clouds can collide and the large clouds eat the small clouds, and you
Sure.
have all the dynamics that's also
Yes.
at play.
But still, the extreme, in the literature, you'll find people talking about clouds that born and die very rapidly. And so let's
And
say,
that's what we see in these low mass clouds. They, or even intermediate mass clouds, they're born and they die within a couple mega years.
hmm, hmm
So
yeah,
you see a spectrum of ages.
hmm
And in Sarah's first paper, she actually showed it's linked to mass. And that's not a new idea, but I think it was shown very clearly in those simulations. And then we see it also in this JFJD plane, that there's a link between the rates that you measure, the cloud mass, and ultimately how long the clouds live.
hmm Okay, well, we're approaching the hour here. Any last questions for Blakesley? Otherwise, I was going to see if you wanted to say anything about the implications for high redshift that didn't have a chance
I'll
to.
say very quickly,
Hmm.
since you asked.
And we do have another question from John, but do the high redshifter first, then yeah.
Yeah, so JWST, everyone thinks it's an infrared telescope, but surprise, it's an FUV telescope at redshift greater than 7. So the ISM is very different at these kinds of redshifts. So the kind of cosmic dawn redshifts, you have much higher temperatures and pressures. You have like lots of, cases of very high star formation rates, very extreme UV fields. And of course, the metallicities can be very different. But my wonderful student, Madison, who's on the call, actually went and looked in a catalog of spectra from the JADES team to try to find some of these FUV lines. And this is an example of the FUV spectrum at different resolutions. So for JADES, we're looking at something like the green line. For the FIM sphere data, like we're looking at something like the red line there in the spectrum. So you can see how, the importance of resolution for resolving the fluorescent cascade. So in the JADES data, we went out and we compared the observed spectrum to model spectrum from the Moudon code. So the JADES survey, right, there's several dozens of galaxies here. We stacked the spectra for all the galaxies greater than redshift 7. These are all observed with NIRSpec. And then we compared them to the reference Moudon spectrum. And we find evidence in the stacked spectra for P Cygni-like profiles for carbon-4, which tantalizingly look like a P Cygni profile that we see in the brightest H₂ FUV line, which is around a little more than 160 nanometers. We also see other lines in our stack that you normally find in the FUV, like helium-2, oxygen-3, carbon-3.
Are the
So
redshifts known well enough to do the stack? So the redshift
yes,
from the
the
spectra correctly?
redshifts, I don't remember what the precision on these redshifts are, but they're all spectroscopic redshifts that have been measured
Okay.
for these galaxies.
hmm
Um, but yeah, the H₂ is sort of interesting. If this is a detection of H₂, then it has a P Cygni-like profile, very similar to the carbon-4. So the carbon-4 here, it must be coming from some kind of outflow, whether it's black holes or stars, we can't really say. I mean, this is again is a stack, so it's sort of an average. We want to do a follow-up where we look at only galaxies with the carbon-4 p Cygni. But right now we've just stacked everything, so we're probably losing some signal with that. But yeah, so this is, I think, an interesting example of how JWST could potentially be used to look for the FUV fluorescent lines at very high redshift.
Great. All right, and last quick question from John then.
Yeah, sorry to hold things up, but I just wondered, I missed the angular resolution of the proposed EOS instrument.
So I think the current angular resolution is something like 200 arc seconds. The idea is that we want to
Okay.
try to resolve some of the filaments on the cloud faces.
Yeah, I was just wondering if it might also be of interest to another completely different community, the people who study evolved stars, because the nearest um, uh, molecular envelopes of mass-losing evolved stars um, have extensive tens of arc minutes,
Right.
perhaps. And it would be very interesting to be able to actually observe the size of the H₂ dissociation zone, because that would help them uh, be much more confident about the mass loss rates, which currently are based mainly on scaling to carbon monoxide.
Right. I'd love to talk more about that with you. I guess it would come down to what velocity resolution do you need to measure the mass loss rate? If our spectral resolution is sufficient for that. So, but maybe we can chat more about
I
that.
think
I'll send.
10,000 is probably good enough, but
Okay. I may still
that's
send you an email if you don't
okay.
mind.
Sure,
That sounds
sure.
really interesting.
Very good. Well, we should wrap up the main session here, but there's a chance to have a more informal chat with Blakesley in a second. So let's thank Blakesley again for a great talk and discussion.
Thank you all.